Hello, everyone. Welcome to the Applied HPC seminar series. Today, I'm going to be talking about an introduction to high-performance computing. So what is high-performance computing? High-performance computing relies on utilizing parallel computing or computing at scale to solve complex computational problems. This relies on parallel processing, which involves the simultaneous execution of multiple computing tasks across various processors designed to speed up computations and increase efficiency. This utilizes multiple CPU or GPU cores, each handling parts of a task concurrently, often utilizing architectures like multi-core processors, distributed systems, or cloud computing platforms. This relies on utilizing a divide and conquer approach where tasks are divided into smaller subtasks, distributed amongst processors, computed in parallel, and then everything is brought back together in a MapReduce where basically all of the data is aggregated into one source of truth. So this requires efficient communication between processors to synchronize tasks and compile results, utilizing mechanisms such as shared memory, message passing, or data distribution. So let me jump into a brief history of high-performance computing. So the beginnings of high-performance computing really start in the 40s and 50s with the invention of ENIAC and UNIVAC. We actually have a picture of ENIAC at Los Alamos on the right. You'll see on the pole at the very most right, a horseshoe hung for good luck. So computing has always been kind of an interesting process where we have a lot of people working very hard to actually make everything work properly. It's not as seamless as you would think. So the dawn of supercomputers began in the 1960s with IBM and CDC 6600. Beyond that, in the 1970s, the idea of vector processing really took off with the Cray and ILIAC form. So vector processing relies on the idea of utilizing a vector of data that you're applying the process to at one time. So this is kind of like a batch operation. In the 1980s, we have massively parallel systems, such as the connection machine in 1985, which introduced massively parallel processing, and the Intel IPSC-1, which was an early commercial hypercube computer. Going forward, we start to see the beginnings of what we know today. So cluster computing, which is the go-to solution for most high-performance computing and cloud computing systems. So Beowulf clusters were basically low-cost supercomputing with commodity hardware. Basically, you grab as many towers as you can and you network them together. ASCII Red was the first teraflop computer at Los Alamos, I believe. In 2000s, the petascale and GPU acceleration really took off. So we have IBM Blue Gene in 2004, which was a breakthrough in power efficient computing. And we have the beginning of the era of GPUs. So in 2007, we had the first general purpose GPU computing infrastructures coming on the scene. In the 2010s, the exascale initiative began with the goal of reaching exascale by 2018. That came and passed, however. So we saw just this year, actually, the first computers which reached exascale with Frontier. So that was the first exascale computer, and that is actually at Oak Ridge National Lab. And we've seen the first ARM-based supercomputers to top the top 500 list as well. What we're really looking towards is next level solutions such as quantum and neuromorphic computing, which can potentially produce additional efficiencies in terms of solving optimization problems. So what is the RCIF CHPC? Who are we? We're not RIS, so we're a different facility. We are specialized in helping researchers solve problems in imaging. So we're really focused on helping people with their healthcare-related AI and ML projects and taking those to the next level with the advanced hardware that we have in-house. We also give white glove support. So we have dedicated support staff available for consultation. Myself and Scott are available to provide you with the best in terms of helping you get started with your projects and helping you go from 0 to 1. Beyond that, we also provide great support in terms of debugging your workflows. We give assistance with application software and workflows, and I actually have a scheduling link where anybody can schedule time with me. So we have on-demand support via Slack, Zoom, and email via support at rcif.westall.edu. We can also help you manage and bring in your own hardware. So if you're a PI and you want to bring in hardware to the CHPC, if you don't want to manage that yourself, we can do that. And we're really focused on helping users take the first steps to go from 0 to 1 on their projects. At the CHPC, we also house a number of shared data sets. So these shared data sets are available for use if you opt into an agreement, basically a service agreement, such that you understand how this data should be utilized. So we have a number of MR imaging data sets and behavioral data. Basically, we have a ton of neuro and cancer-related data sets, which are available for use for training multimodal models or otherwise for training more simple AI models. So these are all available. We can add new data sets as you wish. So we have a form for that. It's very simple to get started. Just to jump into our hardware. So we have really amazing hardware. We have 18 petabytes of storage. This is all on a high trust network. We have about 3 petaflops of compute utilizing a mix of CPUs and GPUs. We have some next level GPUs in terms of being able to serve several H100, A100 machines. We also have an experimental GH200 machine available. So these are all very amazing machines. They're available for use on a tiered system. We even have a free tier. So anybody who's interested in getting started, they can actually come in and utilize the free tier of compute. And then once they have their systems figured out, they can then move to a higher level of service. On the right, we just have a list of the nodes and the resources that they have available. These slides will be available so you can check it out there, or you can check out our hardware at docs.chpc.westall.edu. And this is just kind of a description of the best hardware for the job. So we have different levels of GPUs available, which can solve various problems. The H100 and A100 systems, these are the top of the line and are great for running complex, high throughput computing tasks utilizing PyTorch, CUDA, or any GPU programming framework. To jump into some of the basics of high performance computing, there's a couple of paradigms which can be utilized. So we have CPU-based parallel processing, where we utilize CPU-based cores to solve a complex problem, where we leverage multiple CPU cores, allowing each core to execute different threads or processes simultaneously. This is really good for high memory intensive tasks. So this is great for solving problems where you need a huge amount of memory and you need relatively less compute. High memory, lower throughput, I would say, is better for CPU. One of the considerations is thread management. You have to efficiently manage threads within and across CPU cores. This is often facilitated by advanced operating systems and specialized software that allocate tasks based on CPU availability and workload. The memory architecture utilizes shared or distributed memory models where processors either access a common memory space or have individual memory, influencing how data is accessed and managed during parallel execution. And in terms of scalability, CPU parallel processing can scale horizontally by adding more processors or vertically by upgrading to CPUs with more cores. So this has been the way that people have done high performance computing for a long time. This is a well-vetted method. In terms of workhorses, though, we can really think of CPU-based processing as like a really strong workhorse or an oxen, and you can think of GPUs as a bunch of teeny tiny processors that are really good at working together concurrently to solve a problem. So there's this famous quote from Seymour Cray, If you were plowing a field, which would you rather use, 2 strong oxen or 24 chickens? The GPU paradigm is along the lines of utilizing those 24 chickens to peck your problem to death. In terms of GPU-based parallel processing, it utilizes massive parallelism. So GPUs contain hundreds to thousands of smaller efficient cores designed for executing multiple parallel tasks simultaneously. This is ideal for operations that can be broken down into small independent tasks. We utilize specialized hardware, so GPUs are optimized for compute-intensive, highly parallel computations, and they're more efficient than CPUs for algorithms where processing can be performed in parallel, such as matrix operations or pixel rendering. So the main goal with GPUs originally was, let's calculate the pixel value for an individual pixel. If one pixel is off, it doesn't matter so much because the surrounding pixels will correct for that. This has been kind of applied to GPU computing, but I would say that error handling is much better with general purpose GPU computing than in terms of calculating pixel values. So there's high memory bandwidth in GPUs, which facilitates faster data transfer rates, which is crucial for handling large data sets and textures quickly, significantly speeding up processing tasks. So you have high memory bandwidth, but relatively less memory per thread or per processor compared to CPUs. So CPUs typically have access to much more memory. So for example, if you're running a quad-core machine or a 6-core machine, and you have 16 GBs of memory, you have more memory available than you would on a GPU card. Programming models such as CUDA for NVIDIA GPUs and OpenCL are kind of like lower level programming languages that have been developed for actually running code on GPUs directly. There's frameworks that utilize these as a higher level. So PyTorch, for example, is a higher level framework which utilizes CUDA in the backend and other efficiencies to solve GPU computing problems more efficiently, such as deep learning problems. The main idea is there's some lower level programming languages and some higher level frameworks that utilize those within GPU computing. There's certain fields where GPUs are great. So they're especially effective in fields such as deep learning, graphics rendering, and scientific simulations, where parallel processing can dramatically reduce computational time and increase performance. How can you utilize these amazing systems that we have at the RCIF CHPC? You should request an account. So I would recommend anybody who is really interested in getting started with high performance computing to request an account, and you can actually schedule time with me as well, and we can work through your problems and we can get you started on the CHPC. For anybody who would love to get started, feel free to request an account and we can take it from there. Okay, so let's say that you have an account now. Now what? Part of the process of utilizing the CHPC involves actually logging in. So if you're on campus, you can just SSH in directly to the machines and you can submit a job. The idea is you need to migrate your code and environment. You can submit a job and then you can analyze the data. So it's relatively straightforward. We utilize a batch scheduling system called Slurm. Let's say that you log in and you have a batch script that you want to run. So it's as simple as typing sbatch and the name of the script. In terms of checking your jobs, you can run sq to see the jobs that you have in your queue. And if you want to have an interactive connection to the CHPC systems, you can utilize salloc to connect to an individual machine. Let's say that you made a mistake and you want to cancel your jobs. It's as simple as scancel and the job ID. It's a relatively straightforward system. There is a little bit of a learning curve, but again, we do have documentation and I am willing to sit down to help people go from 0 to 1 on this. Here is a QR code which links you to our documentation. Again, that's docs.chpc.westl.edu. So feel free to check that out. And then if you need more help, if you need somebody to actually walk you through getting started with this, I'm available and you can schedule time with me via my Calendly. So this is my QR code for scheduling time with me. Let's actually walk through the process of submitting a job. The way this would happen is you would actually connect to the CHPC via SSH. You would SSH and log into the cluster, and then you would create batch script where basically you're telling the systems how you want this job to run. So this is an example of a batch script where basically we're telling the system the name of the job, the account that we want to run on, the partition, the number of nodes, the number of tasks, the number of CPUs per task, the amount of memory, the resources that we need, in this case, a GPU or 4 GPUs, the amount of time that we want to run, and how we want the output and error files to be structured. So this header is kind of like something that you set once, and then you can forget it. You just change the job name, the account, and the partition, and then you can reuse this as many times as you wish. The header just kind of explains how you want the job to run. Below that, we can load specific software that we have available on the cluster. So we have multiple versions of CUDA, for example. So here I'm loading CUDA 12.2, and I'm loading my own Miniconda environment. So this environment is called Monai in my case. So I'm just sourcing this, and then I'm setting up some environment variables, and then I'm running a couple of commands just to say my job started on this machine at this time, and I'm running NVIDIA SMI to show what the state of the system is before I start running. And then I actually run the code that I'm interested in just by saying Python -u and the name of the code. So it's relatively simple. This is something that you set up like once or twice, and then you utilize it. And again, happy to walk anybody through this process and spend time with them to get started. So in terms of parallel computing techniques, we've talked about architectures, GPU and CPU architectures. We should now jump into the actual techniques that are utilized. So multi-threading is one of the techniques that's utilized on CPU. So multi-threading relies on concurrent execution. So you have multiple threads which run concurrently within a single process, sharing the process's resources while operating independently to enhance execution, efficiency, and responsiveness. So we're sharing resources. Threads within the same process share memory and resources, facilitating communication and data exchange between threads without the overhead of inter-process communication systems. This relies on synchronization tools such as mutexes, locks, and semaphores to manage access to shared resources. So the most famous example of this would be the global interpreter lock within Python, which basically helps with multi-threading processes and makes sure that you are sharing data appropriately between these multi-threaded computations. So within multi-threading, you can efficiently break down complex tasks into smaller manageable subtasks that can be executed across multiple threads, optimizing resource use and reducing processing time. It's very scalable, so it improves the scalability of applications by distributing workload across available CPU cores, enhancing system responsiveness by allowing intensive tasks to be processed in the background without freezing the user interface. So here we see an example on the right of a single-threaded process, a multi-threaded process, and a single-threaded process with asynchronization. So these diagrams just kind of illustrate how for single-threaded processes, you run a process, you take the data, you run another process, you take the data, and basically pass that along. With multi-threaded, you are concurrently running things in time, but there's a little bit of time delay. So there's different ways of running these single and multi-threaded processes where you have an interpreter lock or a way of facilitating data transfers or sharing data. So beyond multi-threading, we have multiprocessing. So multiprocessing involves two or more CPUs within a single computer system, allowing each processor to execute tasks independently, which enhances parallel execution and improves performance. So we have process isolation in this case. So each process is now utilizing its own memory space, ensuring that processes do not interfere with each other. So this enhances security and stability by preventing one process from crashing others. You would be utilizing load balancing in this case, where you efficiently distribute tasks across multiple processors to optimize resource utilization and reduce processing time. This is often managed by the operating system or dedicated scheduling algorithms. So this also utilizes inter-process communication, such as pipes, messaging queues, or shared memory and sockets to enable processes to communicate and synchronize their operations. This is crucial for tasks that require coordination. This can be scaled effectively by adding more processors to the system, which can directly increase the capability to handle more processes or tasks simultaneously. This is very suitable for high performance and real-time computing applications. So this is more along the lines of what we're doing when we have a job that is running across multiple processors. But again, you could utilize either one of these methods within our computing infrastructure, either multi-threading or multi-processing. So this is just a table on multi-threading versus multi-processing. Again, the core concept with multi-threading is you're utilizing multiple threads within a single process. And the core concept within multi-processing is you're utilizing multiple processes potentially on multiple CPUs. So that's the main takeaway. In terms of memory, threads share the same memory space of the process. Multi-processing, each process has its own independent memory space. So those are the two main concepts which should be remembered from multi-threading versus multi-processing. And there's other concepts here on this table, which I'll allow the reader to go through on their own later. So in terms of GPU programming models now, we can now talk about CUDA in particular, which has been the winner of the low-level computing programming languages. So CUDA stands for Compute Unified Device Architecture. So it's a parallel computing platform and programming model developed by NVIDIA for general computing on graphical processing units. So this is what has really made the difference in terms of the rise of deep learning and parallel processing on GPUs. This was actually a very big gamble on NVIDIA's part, and it took many years for this to actually pay off. So CUDA was introduced in 2006, 2007, and since then, it hasn't really been until the rise of crypto and the rise of deep learning that they've seen a lot of benefit from this. You can utilize CUDA within Python. So it is possible to utilize PyCUDA to interface with CUDA APIs. So this makes it simpler to work with CUDA, but you can do everything that you can do in PyCUDA within PyTorch. So PyTorch is easier to use. It's a high-level deep learning library that provides extensive GPU acceleration. You can actually do anything matrix related that you would be doing in PyCUDA within PyTorch. So you can think of PyTorch as deep learning centric, but you can also do matrix operations within PyTorch as well. So just to compare models, PyTorch is a deep learning library optimized for GPU acceleration. It's especially useful for neural network training. Python is just kind of like the general purpose programming language which you would use to actually write your PyTorch code. So PyTorch is a framework within Python. And then CUDA is the platform and API for parallel computing directly on NVIDIA GPUs. This is tailored for high performance computing needs. I would say for most GPU computing applications, my go-to recommendation would be to utilize PyTorch within Python or PyCUDA within Python. Python is just a really easy to use programming language. CUDA, if you are really good in C and you would love to write some code that is very specific to a problem and very optimized, you can utilize CUDA. But I think the benefit of utilizing CUDA is probably relatively minor compared to just utilizing PyTorch, which has a lot of backend acceleration. So in general, for optimizing parallel tasks, there's a couple of things that you can do. There's load balancing. So you can make sure that you ensure the distribution of workload across all available processing units. So if you have n processing units, you want to balance the problem appropriately. You want to minimize communication overhead. So you want to minimize the frequency and volume of data exchange between processes or threads. So anytime you go from CPU to memory, that has a cost, or anytime you go from GPU to memory on CPU, that has a cost. So you can minimize the overhead of your code by minimizing those communication overheads. Also, optimal use of memory hierarchy is very important. You want to make sure that your computations take advantage of various levels of memory, so registers, cache, and RAM efficiently. So this can include techniques like tiling and cache-friendly algorithms that minimize cache misses and reduce memory access times. Utilizing the fastest memory that's available to you for given tasks on GPU, that can be the on-device memory. If you go beyond that to CPU memory, then it becomes slow. So fine-tuning tasks granularly is also very important. So adjusting the size of the task assigned to each thread or process to achieve a balance between overhead and computational efficiency is a very good thing to do. So smaller tasks might reduce computation time, but increasing scheduling and communication overhead, while larger tasks might underutilize system resources. It's also important to profile and analyze your workflows. So identifying potential bottlenecks and efficiencies in parallel applications is good. So profiling tools or just simple timing is a very good process to try and increase the performance of your codes. Ultimately, that's it for this seminar. I'm happy to take any questions, and I encourage everybody to sign up for the following seminar. The goal is to talk about utilizing profiling techniques to evaluate your code. Feel free to sign up for that seminar, and we look forward to sharing more with you and would love to have you join our CHPC computing infrastructure and utilize our systems to run your code. So happy to take any questions from the audience at this time. Feel
Hey,
free to.
Dennis, can you hear me?
Yeah, go ahead.
Our lab we're currently on RIS, and one of the issues that always comes up is like how to get our data up on RIS. There's storage tiers and all this. We pretty much analyze like large genomic data sets on the order of, say, 500 gigabytes. Like, how easy or difficult is it to like mount a local lab server storage or to, I guess, just copy data up to HP, your computing environment?
Yeah, so that's something that we can definitely work with you to achieve. There's a couple of solutions for this. We can utilize direct data transfers through SFTP, or we can utilize Globus, which is something that we're implementing at this current time. That way, you can just focus on computing. So we can help migrate your data in and make sure that it's as smooth as possible.
Okay, thanks.
And if you'd like, feel free to set up a time with me. You can email me directly and we can set up a time to chat about this. My email is dennist, DENNIST, at westel.edu. Are there any other questions from the audience?
So we have just like one kind of monolithic storage system.
Yeah, so we have like one kind of monolithic storage system, all based on Ceph. It's basically mounted across a number of different laboratories as well as across our computing infrastructure. So most people that need to compute on a data set can do so in their labs, they can do so on the CHPC, and it's all contained in the same place. And as Dennis said, there are many ways of getting data up into our storage system. We have a page on our documentation, and I'll post that here in the chat.
All right. Well, thank you, everyone, and hope you have a great day. This will be available on YouTube for viewing later. And again, feel free to check out our documentation or our GitHub repo. So thank you, and